Everyone, maybe good morning. I would like to welcome you all to this second session for Pipesim fundamentals. In the past session, we talked about Pipesim fundamentals in general. We went through the Pipesim user interface. Before that, we talked about the importance of flow assurance in any production system. And we also showed a demo on Pipesim, both wells, well part and network part. We showed the GIS canvas, we ran a simulation and so on. Today, we will be focusing more on wells. And even in the last session, we had probably two slides about the concept of nodal analysis. I will also speak about nodal analysis in a bit of detail today. And then I'm going to move to Pipesim. I hope that you enjoyed today's session. So in Pipesim is used actually to model production systems, production and injection systems, in addition to the pipeline facilities. So if you have, for example, a field that is composed of 20, 30, 500 wells, you can model each well separately in Pipesim. And you can model also all the pipelines connecting the wells together into the gathering manifold and probably into the separation facility and maybe the sale point. Today we are going to focus on the wells. And when we talk about the production system, we're talking about an individual well, not connected to any pipelines or any other wells on the surface. So this is a well cross section or a production system cross section where the production, as we all know, starts from the reservoir, where we have flow through the porous medium, right? And then the production, the flow, the hydrocarbon will go into the completion, and then to start climbing up, passing through any downhole installed equipment. It could be downhole choke, it could be subsurface safety valve, etc. And then we go to the surface choke where normally it's used to control production. Also on the wellbore, we could pass through artificial lift, such as electric submersible pump, nitrogen lift, gas lift, PCP, sucker rod pump, etc. And then the flow will go over the pipelines until it reaches the separation facility. Okay. Now, we need to understand how and what are the main parameters that will affect the production. Of course, the objective of any oil and gas asset owner, whether it's a national oil company or an operator, they would like to maintain the well productivity along a very long time of the well history. So from drilling till abandonment, you need to maintain good production, good flow rate, but at the same time, we need also to look into the the reservoir, what we call it, the reservoir conditions. Meaning, we need also to not only to focus on the well only, but also to the reservoir, to the reservoir as a whole, to be able to extract the maximum out of the hydrocarbon reservoir. Okay, and this is what we call the recovery. The recovery is the percentage of the oil that you can produce from a reservoir. And usually, we cannot, as we cannot extract all the oil coming from the stored in the reservoir. Good percentage of recovery rate is something like 50%, 60%. And as we increase the recovery percentage, then we of course will get more oil. And it's always very wise to drill the completion very well, to control the production so that we don't invite water or gas. And once we invite water or gas from the reservoir, then this will destroy the recovery from around the wellbore. Okay. So it's all about pressure. It's all about the production in the well is all about pressure. Pressure is the main driver, the main energy source that will push the fluid from the reservoir to the surface facilities. Okay. Now, pressure drop in the total system at any point is the reservoir pressure minus the last pressure value in the facilities outlet, which is the separator pressure. So this is the total pressure drop. We're talking about, again, we're talking about a single well, just focus about a single well. Then, as I said, pressure drop is the uh, driver that will make the hydrocarbon flow from the reservoir to the surface. Okay. So delta P total is P reservoir minus P separator. This is the total pressure drop in any production system, any individual well production system. This is the sum of the pressure drops occurring in all system components. Okay. And if we really need to think about all the pressure drops, across the let's say production system, which is P reservoir minus P separator, this equals delta P in the reservoir, or what we call the drawdown, for the fluid, for the hydrocarbon to move from the reservoir until it reaches the bottom hole, right? Then we have delta P across the tubing. We have delta P in the choke. We have delta P in the flow line. Delta P in the tubing could be also many components. And this delta P could be negative, because if we have, let's say, artificial lift, then we are actually removing from the load that the fluid will pass through, because the artificial lift is an additional, is a positive pressure drop to the fluid, which means that we don't call it pressure drop, it is pressure gain. And that's why if we need to add the artificial lift element here, it will become negative. Okay, so this is the total pressure drop. And as you can see here, we can have a lot of other elements that we can add to this equation. Okay, now let's talk about the basic and the most principal theory for nodal analysis, and how nodal analysis was successful in predicting well production, well performance, and how nodal analysis can be used in production optimization. Okay, so let's assume that we have a pipe, right? The pipe, it has a fluid. The fluid moves from left to right. And let's take one node, we call it, at any point arbitrary along this pipeline. Now, pressure drop at the selected node, the pressure value at the selected node is calculated from, so how can I get the pressure at this node, right? So it's really simple. If I know that P upstream of the pipe, P downstream of the pipe, and then I am able to calculate the pressure drop upstream of the node and the pressure drop downstream of the node. Then I can, of course, get the P node, right? Of course, I mean, this is obvious. So pressure at the selected node, P node, is calculated from P node equals P upstream minus, of course, delta P upstream components. So if I have many components here, I would say P node equals P upstream minus delta P upstream. At the same time, P node equals what? Equals, P downstream plus delta P downstream, because this pressure at this node is higher than the downstream pressure. Higher by how much? By delta P downstream. So again, I am calculating the pressure at the same node, but using two sides of the flow. The upstream side of the flow and the downstream side of the flow. So I can say P node equal P upstream minus delta P upstream. And also P node equals P downstream plus the delta P downstream, correct? This is, again, until now is really nothing. This is very logical, very easy, straightforward to understand. Now, delta P varies with flow rate. So now how can I know, again, this is my question. How do I know the pressure at this node? Because until now, I haven't solved really the problem, okay? Because the pressure here has to do with the flow rate, okay? So delta P actually varies with flow rate. So what do? I need to vary the flow rate. So what I do is that I plot P node versus Q, all right, for the inflow to the node, and delta P node versus Q using the outflow from the node. Let me just explain it a little bit further. So what do? As I said, I have these two equations: P node for the upstream, P node for the downstream. Okay. So I start assuming flow rates. Okay. And I say, okay, now by the way, I know P upstream and I know P downstream. What I need to calculate P, the delta P for the upstream, delta P for the downstream. What do I know? No, I know the flow rate and I know the pipe size. Okay. So I start assuming values. For example, I say 10 barrels. How much is the delta P upstream? Then I can say that at 10 barrels, P node at 10 barrels, P node from upstream is this value. And again, at 10 barrels, P node from the downstream is this value. And that's why I will get, for example, one value here. This is for 10 barrels, another value here for 10 barrels. Okay, this are my two points. And then I start to increase the rate. All that is iterative. So I say, okay, for 100 barrels, how much will be delta P upstream? How much will be delta P downstream? And then I calculate P upstream, P downstream, and then I get 2 more points. And I continue. 100 barrels, 200, 500, maybe 1,000, maybe 2,000, and so on. And then as you can see here, I draw this curve here that represents what? It represents P node from the upstream point of view at different flow rates. And at the same time, since I have assumed many flow rates and I calculate P node from the downstream point of view, I will have, because as you can see here, the as the flow rate increases, this delta P will increase, right? Because I have more pressure drop. So now P node will start to increase because as the flow rate increases, I am adding, right? I'm adding a positive component that's increasing. And that's why this curve will go up. And this curve from the upstream will go down. Okay? Now I have two independent curves. Okay? But now if I tell you from Mathematics 101, okay? If I have two curves and I need to define one point that for these two curves that represents the same X and Y, what do they tell me? It is the intersection. Why? Because P node, no matter you calculate it from the upstream or from the downstream, will be the same. So the same pressure and of course the same flow rate. And that's why we have two curves that are calculating P node but at different rates. And I need to know how much, if I have a fixed rate, how much is P node? Basically, I find the intersection. So the intersection is how much is the pressure at the node, and this will give you also the flow rate. I hope this is clear, because this is the most principal idea for nodal analysis. Okay. Now let's move on. So again, we're talking about the production system, right? So having this idea of, this idea basically, P node equals P upstream minus delta P upstream. P node equals P downstream plus delta P downstream. Just keep this idea in your mind. Now think about a well, right? In this well, we can, number one, talk about what are the parameters that will affect any production system, okay? Because it's composed of a reservoir, area around the wellbore, casing and tubing, restrictions, wellhead choke, flow line, joints, elbows, valves, etc. Right? Now, and then finally the separator. So what we can do, we can split the production system into two parts. One part is the inflow. This, and I'm going to select my node to be at the bottom of the well. Remember this idea again? The idea that I talked about, when I described here. So this is my node, right? So what I'm going to do now in the well, I'm going to select my node to be at the bottom of the well. And then I'm going to calculate. So this will be my upstream to the node components. And this will be the downstream, the downstream components of my node. This is my node, okay? So now I'm going to use the same approach, okay? I'm going to apply the same idea. So if I'm going to talk about the inflow now, which represents basically P upstream minus delta P upstream, because this is my node, this is P upstream, this is delta P upstream, correct? So now let's do the same. Let's find out how can we draw this curve that represents the pressure at the node by varying the flow rate. Okay, so let me just start with the first point here. So I'm gonna make a plot for P versus Q, and again, P is the pressure at this node, right, versus Q, which is the flow rate. So I'm going to vary flow rate, right, and then calculate delta P across the reservoir, and from which I'm gonna get the PWF, which is P will flowing pressure. So the first pressure, if there is no flow rate, is what? If there is no flow rate, there is no drawdown. So delta P is 0, right? So delta P is 0. That's why the first point is P reservoir. What will happen as I increase the flow rate? I'm going to have what we call drawdown. Drawdown. As the flow rate increases, drawdown will increase, correct? So I am increasing the flow rate on the x-axis. So drawdown will start to increase, and hence the flowing bottom hole pressure will start to go down. And then this is what I need to call the IPR, inflow performance relationship. Inflow performance relationship. This is the IPR curve, okay? And it's a representation of, the pressure drop in the reservoir and across the completion. If I have a skin, if I have perforations, etc., all that will be taken into consideration in the drawdown calculation. So, good. So now, let me just remind you about a very nice concept. If I have a straight line, all right, and by the way, this straight line happens if I have only single phase. The moment I reach the flowing bottom hole pressure, then the curve will be shifted like that, like this on a concept we call Vogel correction. Okay, so let's assume that I have 2 points on the straight line, P1 and P2, and then what is this? This is delta P, correct? And then I'm going to take also the corresponding Q, which is the flow rate, Q1 and Q2. So this is delta Q. So now if I ask you from your elementary school, what is the slope? What would you tell me? Slope is delta Y over delta X, correct? What is delta Y here? Delta Y, we'll do this again. Delta Y is delta P. Delta X is delta Q. So this is the slope, right? So I have delta P, I have delta Q. I can calculate the slope, correct? Of this straight line. But now, what is the productivity index? Productivity index is the inverse of the slope, which means delta Q over delta P. And that's why the unit for productivity index is what? Is barrel per day per PSI. Unit for the productivity index is barrel per day per PSI. This is in the field unit. Okay, and if it's metric unit, then it's going to be meter cube per second or meter cube per day per, you know, I don't know, bar or Pascal, right? So this is interesting because this is now, we understand now how the IPR curve is related to the productivity index value, okay? So let's do further understanding. So this is the IPR, this is the inflow performance relationship, correct? So now let's ask ourselves, what are the factors that will affect the IPR curve? Remember, this curve is drawn by basically changing flow rate on the x-axis and calculating flowing bottom hole pressure, which is P reservoir minus delta P the reservoir. Put this in your mind, okay? So now when you think about the factors that will affect the shape of this IPR curve, number one, you would see that P reservoir is very important. Why? Because P reservoir is the starting point of this IPR curve. The higher P reservoir is, the curve will start from a higher point. The lower P reservoir is, the starting point will go down. K is the permeability. Okay? How would the permeability affect the IPR curve? Well, I don't know if you remember, but this is the definition of J, which is the productivity index. It has to do with the you know, K, which is the permeability, the height, and this is basically taken from Darcy equation. The viscosity, formation volume factor, and the radius. So all that is taken into consideration because it affects the productivity index. And as we all said, the slope of this line is the inverse of the productivity index. So fluid properties, K, viscosity, the completion design, completion length, whether it's perforated, whether it's vertical or horizontal, whether it's you know, multilateral, etc. All that affects the productivity index. The skin value. The bubble point is very important. Why? Because it defines the straight line and then the Vogel correction below the straight line. The drainage area, okay, because all that is taken into consideration into RE. So as you can see here, all these will affect the IPR curve. So for higher reservoir pressure, the starting point will go up. Lower reservoir pressure, the starting point will go down. Higher K, higher permeability, the slope will be less because the productivity index is higher. Higher skin, the slope will go down, and so on and so on. Now, we're done with the inflow, okay? Keep these ideas in your mind. And now let's talk about the outflow, okay? So the outflow, this is the outflow. And I would like to, yes, you can raise your hand, tell me. You can speak up. Hardik, you're muted.
Yes, sir. My question is how we can, how the completion affects inflow. I mean, if you are mentioning if it is vertical, if it is horizontal or directional, then I think basically what is changing is the drainage area only. Because in vertical well, the drainage area would be less. In horizontal, the drainage area would be high. Other than
No,
this,
but
I don't think.
yeah,
Other than this, yes, sir.
yes. You have studied, you know, the let's say the horizontal IPRs like Joshi, Babu and Ode, etc. So all these, the well length will be taken into consideration because you see, if it's
Okay,
vertical, because as we all know, we have we have what we call the anisotropy. We have the horizontal permeability and the vertical permeability. Okay, so now
yes, sir.
when you have vertical completion, right? The exposure of the you know the open hole
Well-bow.
will
Yes,
be less, right? So although
yes,
I am in the same drainage area, but if I drill vertically or horizontally or in an angle, all that will affect the calculation.
absolutely. So
That's why
it's nothing related to the completion in tubing. It's basically how much area is exposed of the well-bow
we call it partial
behind. Like
penetration.
yes,
We have what we call the partial penetration skin, all right? So all that is
absolutely.
taken into consideration. In addition, for example, is your completion Is your completion open hole? Is it, slotted liner? Is it perforated? So all these will be taken into consideration, right?
Okay, sir. Thank you.
Yeah. So now talking about the outflow, and please, I mean, let's make this interactive. If you have questions, please go ahead. So in the outflow, we are now going to recall from P node equals P downstream plus delta P in the downstream, correct? This is what we described the first point. So this is P node, and let's assume that we're stopping at the wellhead for the time being. So we say P node equals P downstream, which is P wellhead, plus delta P in the downstream components, correct? P bottom hole equals P wellhead plus delta P in the tubing. Now, what is delta P in the tubing? Delta P in the tubing has two components now. Has delta P due to friction and delta P due to elevation. Not only that, let's expand more. So delta P due to elevation is what? Is rho GH. This is the hydrostatic pressure, correct? This is the hydrostatic pressure. Now, if I keep this in my mind and I start thinking about how do I draw the outflow curve now by varying, the flow rate, then what will be, remember when I asked you about what is the first point when there's no flow rate in the inflow? We said the first point is the reservoir pressure. So now, if you know the answer, raise your hand. Considering this equation, when there is no flow rate, what will be the first point, the first pressure? There's zero flow rate now, okay? So what is the first pressure? What do you think? Anybody? So when there is no flow rate, I cannot see anybody raising their hand, but I don't know. Maybe I don't see everyone. Yes, Hardik, go ahead.
I think P wellhead is equals to P flowing bottom hole pressure.
No, because you see, so this plot is for flow bottom hole pressure, right? And now I'm saying that there is no flow rate. So out of this, the only element that will disappear is delta P friction. Rho GH will still be there. Okay, so that's why the first point is PZ plus P wellhead. So if somebody asks you, want to ask you about, okay, give me the static bottom hole pressure, and he gives you the wellhead pressure. He tells you, okay, the wellhead pressure now, the well is closed, there's no flow rate. The wellhead pressure gauge is reading, let's say 50 psi. Can you calculate for me the bottom hole pressure? The answer is yes. I add, because I need to know the fluid, of course. I need to know the density. If I have any gas, if I have any water, now assume that this is all average density. And then I know the depth. So that's it. Rho GH. This will give me the hydrostatic pressure. I add to the wellhead pressure. This will give me the static bottom hole pressure. Now, what we found is that when we start flowing, right, you will notice something is interesting. This is what we call the VLP, vertical lift performance, or outflow curve. So it is clear that as the flow rate increases, this part will increase. The friction will increase, right? For more flow rate, more friction. And since this is positive, then that describes the curve going up as the flow rate increases. But we always notice in nodal analysis that in the beginning, there is a small dip that will make the flow and bottom hole pressure in the beginning less than the static bottom hole pressure. So let's give you an opportunity. Anybody, any idea why this happens? considering this equation? So anybody raising their hand? Anybody can try? Why there is this dip here? Okay, as I said. So Hani Ibrahim, تفضل. Hani.
This is used when we kick off the well. So this is an unstable condition for the well.
Okay.
For this reason, it has decline and then it started to build up when we have a steady flow from the well.
So you describe what happens, but you didn't describe why. You're right, by the way, but you didn't describe why this goes down.
Because of the instability for the pressure when we started to kick off the well.
Instability. I mean, how does instability reduce the pressure? Let's give more chance to other people. So see, okay, Hani, Muhammad Mansour.
Yes, this is because of this is because of having low velocity, and the density is like the dominant of this behavior. Once we have more Q, more velocity, so the friction will be the most dominant, and we have that
Excellent,
straight
excellent,
line.
Excellent. But I need more. So you mentioned very important elements here. You mentioned velocity is small, and then you said that density is the most dominant. But I'm still waiting for why this happens. You're right, but why the density is dominant now, and then why at this point here the pressure is less than this point. So yes,
so velocity
is low. Yeah.
Can I try?
Yeah, try please.
I think because at the beginning the well is closed, so there is no more pressure and the rate is going down.
No, you're talking about the pressure transient concept. No, we're assuming.
I think you're pointing to liquid hold up, maybe.
No. Can I try this one, Ahmed?
Go ahead, please.
Okay. On the beginning, we are talking about the static pressure when the well is closing. So the BWH will be the highest level. Then when we start to flow the well, the flowing pressure will be affected by the drop on the wellhead pressure at surface, while the friction is very minimum. So for this reason, it's decline little bit until we have the drop between the reservoir and the flowing, and then start to build up until we reach the flow to the surface.
So for the sake of time, because we need also to demonstrate Pipesim, I'll give an answer. The best answer I heard is from Mohammed Mansour. What happens is that in the beginning, the velocity of the flow is small. Why? Because flow rate is low, the tubing size is large enough. So in this area, in this region, also this is also I think what Mr. Hani has mentioned also, it's called unstable flow. What is the characteristic of unstable flow? When the velocity is not high enough, we call it the well is not loaded enough. So what will happen is that the gas will segregate more in the wellbore. The liquid doesn't have enough energy to flow steadily with the gas. Because the velocity is low, all right? The oil is heavy and it requires certain velocity to gain kinetic energy so that it will flow steadily to the surface. When the velocity is not enough, the liquid, the oil doesn't have this enough energy. And that's why, there will be more gas coming from the reservoir will climb in the wellbore and fill the wellbore. And that's why the density will become less. So that's why, and again, the rest of the gentlemen mentioned that. They said that during this, in the beginning, all right, it is density dominant, meaning the density will become less. Because if I compare the gas fraction in this, you know, when the well is closed, it will be less than this point here. Because what we're doing right now in this point here is that well is not loaded yet, it is not stable yet. So we're inviting more gas. The gas will become more in the wellbore until, you know, we increase the choke a little bit more. Then there will be more oil coming from the reservoir. Then the well is loaded. Then from this point upwards, it's going to become the delta P is the main dominant for the outflow curve. Okay. Now we're passing a lot of time, so let's continue. So now, considering this equation here, what are the factors affecting the VLP curve? We know that the wellhead is affecting the VLP curve from this equation here. The inside diameter, the roughness, the density, GOR, water cut, API, the well depth, and the artificial lift if we have artificial lift. Okay. So now, for higher water cut, now you need to think a little bit. For higher water cut, we notice that the VLP curve will go up. Why is that? Higher water cut, VLP curve will go up. Why? Because density is higher. Higher water cut, density is higher. And then if I add a positive value here, this bottom hole pressure will start to increase. So for the same flow rates, the VLP curve will go up for higher water cut. Similar concept, higher GOR, density will become less, so the VLP curve will go down. If I have higher wellhead pressure or a deeper well or heavier fluid, all the VLP curve will go up. All that is described by this equation here, correct? So this is excellent. So now, that's now the beauty of nodal analysis. We draw the IPR curve separately. We draw the OPR or the VLP curve or the outflow curve separately. And then you find the intersection. And the intersection describes the operating point. So this is how nodal analysis works, okay? So applying the nodal analysis concept in, now this, we'll see how this really describes many known facts in the well productivity. But now the nodal analysis can describe it very well, visual, in a visual sense. Like for example, we know that if the water cut is lower, what will happen to the production? What do you think? Lower water cut, higher production, right? But why is that? Because lower water cut affects the outflow curve. Lower water cut means lower density, and it means that the outflow curve will go down, and then the intersection will go to the right, and that's why we produce more. See now how beautiful this is? Higher productivity index. We know that if I have higher productivity index, the well will produce more. But why is that? Because higher productivity index means lower slope, means the IPR curve will go up a little bit, and then the intersection will go to the right. Higher GOR. For higher GOR, I produce more. Why? Because I have lighter fluid. So this value will go down, and then the bottom hole, the outflow curve will go down, then the intersection will go to the right. I produce more. Smaller tubing ID. Smaller tubing ID will create more friction. It will block the production. And that's why we produce less. But of course, in the beginning, we are starting from the same point because there's no hydrostatic effect. Deeper well, for the same conditions, same reservoir pressure, same wellhead pressure, same fluid, if the well is deeper, we are going to produce less. Why? Because rho GH is higher due to H. And then the outflow curve will go up, and then the intersection will go to the left. Higher reservoir pressure, we produce more. Why? The IPR curve goes up, intersection goes to the right. See how beautiful this is? For higher wellhead pressure, I am choking the well. The production will go down. Why? Because the outflow curve will go up due to the wellhead pressure, and then the intersection will go to the left. This is why nodal analysis is very powerful. Okay. So now a plot of P, a plot of P versus Q, sorry for this plot, gives you the production. And then let me just skip this quickly because I need to go to Pipesim now. How far can we increase the tubing size? So I mentioned that the tubing size can affect the production, but it's very important that as I increase the diameter, the outflow curve will start doing something like this. And then once at one point, okay, the intersection will happen on the left-hand side of the VLP curve. And this is what we call the unstable condition. We don't want that. And that's why it's not always nice to start increasing the tubing size. There has to be an optimum tubing size, all right, beyond which there will be no enough velocity for the oil to go up. Optimum horizontal length, again, there will be a point where as you increase, for example, the horizontal length, you will gain more and more, but until one point, it becomes really not very useful. And then finally, application of nodal analysis. So you can use it for selecting tubing and flow line size, sizing chokes, surface chokes, subsurface safety valve, artificial lift design, completion design, etc., etc. And with that, let's go now to Pipesim. I know that this session is for about Pipesim, but I felt I really needed to go to this introduction before going to Pipesim. Is there any question before we fire up Pipesim? So let's start Pipesim then. So this is Pipesim interface, okay? So when you open Pipesim, you can have either network perspective or well perspective. For well perspective, we can go create a well-centric workspace, all right? Now, I need to indicate that if you go to help, right? If you go to help and then you go to case studies, you will find a lot of ready-made case studies that you can look into, right? And have an understanding about different, examples of models. So I have well models here, and if I click on double click on well models, I can see that I have a lot of examples for wells, right? So let us start with the simplest one, or I'm going to, I'm going to build a well model with you, okay? And then we can look into the examples later on. So I'm going to say now, I'm going to say new well, right? So this is what will happen when you start to build a new Pipesim case. In Pipesim, we have 3 tabs here. We have home for the tasks, we have insert, and we have format, okay? Insert, where you can actually add equipment to your well, right? This is interactive, and so that you can drag and drop directly, and then you follow these tabs from left to right while you're building your well model, okay? So now let us start by saying general. I can call this name, this is my first well, okay? Now here I can define whether the well type is production or injection, all right? And now if there is a check valve, I can put check valve here, and I can add comments, okay? So this is not necessary, this is just optional. So now let us start by adding casings, okay? So I'm gonna add my first casing here, okay? So this casing is assumed to, by default, it goes to 10,000, okay? And I can, of course, change that by going to the tubular. Now, as you can see here, I have the casing and liner, and I have tubing. I have not added any tubing yet. So let's assume that I have one casing that goes all the way up to, let's say, 1,000. And then I'm going to add another casing that goes to, let's say, 5,000. And then a third casing that goes up to 7,000. And then this is my, so this is my last casing. And then I'm going to add a liner. So what is the liner? The liner is, you know, a casing. It's a piece of pipe that you extend at, you know, after your last, let's say, casing, and it is basically hanged or connected to the last casing. To maybe you can use it now for to put your perforations, etc. Okay, this can be either a liner or it can be also open hole. Okay, so this is at the end. Now let's make it as liner. And now at each of these, we have the diameters. Okay, so let's start from the top to bottom. So now this one, maybe the inside diameter is, let's say, maybe 20 inches. And then it's going to be, let's say, 16 inches. And then it's going to be, let's say, 12 inches. And then my liner inside diameter, let's say, is 7 inches. Okay. And as you can see here, in between, all right, I can define what is the material. Like, for example, if I go to casing, I can define the annulus material. This is used for in the heat transfer calculations. Okay. So cement top, all right, cement density, cement thermal conductivity. Okay. And I can add also the thermal conductivity here for the casing itself. And I also can add the borehole diameter. All right. This is again, if I want to calculate the heat transfer, the transfers. All right. So this is simulating the drilling program, my drilling program. So initially I have a large drilling bit. Of course, you know, the numbers may not be very practical, but this is just for demonstration. So I have first 20 inches, and then 16 inches, 12 inches, and then 7-inch liner. Okay. Now I have added my casing. What's next? I need to add my tubing. So I would just drag and drop like this. And then this is my tubing here. So the tubing will go all the way up to 6,800, for example. And now the inside diameter is, let's say, 3.992. So now this is my well cross section. Of course, now I need to add a packer. This packer is to block the fluid from entering into this annulus space between the tubing and the casing, right? So I'm going to drag and drop a packer. Okay. Now this is my well cross section. Good. So now what is next? So I have entered my tubular. I now need to enter my deviation survey. So depending whether your well is vertical or 2D or maybe 3D, okay? Let's assume that I have 2D now, okay? The reference options, now this depends on, you know, whether you are offshore, onshore, etc. There are different depth references. You know, if you need to learn more about these, you can go to the help, and then you can define your wellhead depth. now you can start entering your deviation survey. So let's quickly, for example, 0, 0, and then it becomes, let's say at 4,000, this is where my kickoff point starts. And then I'm going to start entering. So as I move down, the measured depth will become larger than the true vertical depth. So I'll just enter, for example, at 5,000, what will be my TVD? At 6,000, what will be my TVD? Sorry. And then at 7,000, what will be my TVD? Okay. And then at last point, which is 7,700, what will be my TBD? Now, as you can see here, Pipesim is not happy because I have not defined my measure depths, okay? So I can now define how I'm going to describe my deviation survey. The dependent parameter, it's either the angle or the MD. Okay, so now I have defined my TVDs. Now at 4,000, now at 5,000, I can say that now my angle now starts to deviate. So it becomes, let's say 12. And then it becomes 45. And then it becomes, let's say 65. And then it becomes 85. So now automatically, as you can see here, it calculated for me my MD. And of course, if I have a table for my deviation survey, I can copy and paste here, okay? And it can be also more points if I want, okay? So I am now describing almost a horizontal well, right? Then I have a liner. I'm assuming that possibly that I can have maybe, you know, my perforation will be at this point, okay? So let's continue. Do I see any questions or chat? Okay. So I have now entered my wellbore, description, casings, tubings. I have entered my deviation survey. Now for the heat transfer, I can simply, you know, specify the heat transfer coefficient, all right? Where I can say that, okay, my heat transfer coefficient is 2 BTU per enthalpy per degree Fahrenheit per foot square. Or I can ask the software to calculate that for me. And if I want to do that, then I need to enter the ground density, the ground, conductivity, etc. But let's keep it simple at the moment. And now let's just specify one value, all right? Tubular is done. Done all equipment. I have only one packer, all right? I don't want to install any of the other equipments. At the moment, I will not add any artificial lift. Now completion. So I need now to drill a completion. So I go here and then I add, drag and drop. I'll put the completion at the liner. Okay. Now it will start to complain because it is missing all the information related to the completion. Click on this one. And now you can see that it is complaining about the reservoir pressure, reservoir temperature, and the productivity index. All this depends on the IPR model that I select. Okay, so there are different ways to describe my IPR models. Each of these models will be used to calculate the drawdown or the pressure drop. Okay, so this can be listed here based on the geometry profile and the fluid entry. Okay, if I say that my geometry profile is horizontal, then it will be turned into the horizontal IPR methods, the steady state and the pseudo steady state methods, Joshi and Babu and Ode. And this is for the single entry, what we call a single entry IPR. or I can make it distributed, due to Zoom, because I'm sharing it, my machine is slow. So if I say distributed entry, then I need to define the starting point, the end point, and now I have now a new method called distributed PI or trilinear transient IPR. Trilinear transient IPR, this is for unconventional resources, for shale formations. So let's go for the simplest now, and let's make it again, let's make it single point, vertical, and then PI. So the reservoir pressure, let's say the reservoir pressure is 2,800. Reservoir temperature is, let's say, 190 degrees Fahrenheit. The IPR basis is liquid, so productivity index is maybe 5 barrel per day per PSI. Now, these options, I'm going to show you the effect in a moment. So what is still complaining about? It's complaining about the fluid. I have not assigned fluid to the completion. So I go to the fluid model, and then I'm going to click on new fluid. I can add an existing template, like for example, dry gas, light oil and gas, heavy oil and gas. Let's go to light oil and gas and click on OK. Now, this is the template for the fluid, okay? So I define the water cut, the gas oil ratio. Let's say the gas oil ratio is 500 standard cubic feet per subtank barrel. This is the gas specific gravity. Let's say it's 0.85. This is the water specific gravity, and this is the API. So let's make it more practical to be 35. And this is if I have any impurities. This is the viscosity options, calculations, all the correlations for calculating the viscosity. I can even specify my viscosity if I want, etc. If I have any fluid calibration points where I can measure the fluid, let's say I have the formation volume factor, I have the saturation pressure, etc. Or I can still leave these correlations to calculate all these properties for me. No need for calibration. So that's it. I have defined my fluid now. And now there's no validation errors. Now I am ready to run my first case. Okay. So I go to Home, and then I go to Nodal Analysis tab. He will ask me about where do you want to put your node. I tell him bottom hole, because in theory you can put your node at the wellhead, right? Click on OK. And now he's asking me about what is your outlet pressure. Let's say my outlet pressure is 250 psi. And now I click on Run. So this is my beautiful inflow and outflow curves. And this is my intersection point. This is the operating point. And the operating point here is defined by the flow rate and the flowing bottom hole pressure. So the well now should produce 5,784 stock tank barrel per day. And this is in stock tank conditions. This is what I'm going to see at the surface, okay? And this is the flowing bottom hole pressure. Where? At this point here. As you can see here, this is my nodal analysis point, okay? Now, let's play with the nodal analysis. So if I tell him now, what is the impact of changing water cut? Remember, as the water cut increases, what will happen to the production? Production will go down. Why? Because the outflow curve will go up. So let us see that. So if I go to completion and I go to the water cut and I say, okay, 0, let's say 25 and 50. And I click on Run. So as you can see here, sorry, I said as the water cut increases, the VAP will go up, okay? So this is obvious here. When the water cut, me just expand this a little bit. Okay. So this is water cut of 0, all right? And as you can see here, the water cut, by the way, don't be fooled with this inflow. So we're having multiple inflows on the same plot here. Look into the outflow curve. So this is outflow of 0, representing this curve here. And this is the intersection. This is the outflow of water cut 25, and this is the outflow of water cut 50. As you can see here, as the water cut increases, the VLP curve goes up. Not only this, I'm going also to have what we call the profile results. Profile results represents, different curves at different water cut. This is at 0, this is at 25, and this is at 50. As you can see here, the two boundary conditions are the same, but the curves are different because I have different pressure drop, because I have different flow rates. This is the system results, okay? Now, let me do something interesting. So let us go now to the completion. So this is my reservoir. Remember I told you about these checkpoints? So now I have checked by default, use Vogel below bubble point. If I uncheck this will be my straight line, okay? But now in reality, the software will go to my fluid description and understand where is my bubble point. It seems that my bubble point is somewhere here. And then after the bubble point, Vogel will play a role in actually making this curve. This curve behavior, or the deviation from the straight line, will be more severe as the GOR increases. Let me show you. If I go now to the fluid model and I go to override method, I'm going to override the phase ratios. Originally, the phase ratio was 500, correct? So if I'm going to increase the GOR and I say that it is 1500, and I go back to my IPR curve, I see now that it is more curved compared with previous. Okay. Now, we have now something called Vogel water cut correction. So as the water cut increases, then, the water cut is what? Is water compared with oil, okay? As more water cut I will have more water than oil. So the effect of gas-oil ratio will become less and less, correct? So you'll notice that if I go now, so look into this curve. I'm going to take a screenshot. Now we'll keep it aside. Now I go to my fluid model. Let me just uncheck use Vogel water cut correction. So I go now and I make this water cut to be 60%. Look into what will happen now. So the moment I click on Vogel water cut correction, the IPR curve will be a bit different. And let me show you the difference here. See, you will notice that, it becomes straight line, and then, the effect of the gas will become less. This can be also be seen if I go to my nodal analysis again, while this is checked, and then I'm going to leave the same values. Now you'll see now an interesting thing into the inflow also. See now? Now my inflow is also affected by the water cut. So the water cut is not now only affecting my outflow or my VLP curve, it is also affecting my inflow because I checked this option here, right? Any questions so far? So this is what we call the nodal analysis in Pipesim. Okay, and as I described earlier, I wanted really to go through this nodal analysis theory to give you flavor of, you know, when Pipesim calculates the inflow and the outflow by using different sensitivities. And I can of course, you know, remove that, and now I can add an outflow sensitivity. Like for example, I can tell them, okay, change for me the outlet pressure, the wellhead pressure, and then the default wellhead pressure 250. So I'll tell them, okay, give me 250, the impact of changing the wellhead pressure, 350, 500, okay. And then let's also make the completion let's say I put the water cut of 50, for example. Now you see that because you know the doesn't allow me, because the water cut is actually used in both. Okay, so let's just remove the water cut, and then let's go to the again wellhead pressure. So 250, 350, and 550. Okay, click on run. As you can see here, the outflow is affected directly by the wellhead pressure. What if I change the PI, productivity index, 5, 20, 100? Run. You'll see now I have all these points here, and if I want, I can you know, I can zoom. Sorry. I can zoom like this. Still running. See now, these are different outflow curves representing different wellhead pressure, and this is different inflow curve representing the productivity index. And then I can now later on select my future production, for example, as the water cut increases, as the wellhead pressure increases, as the reservoir pressure increases, etc. And then I can represent it to my management for actual decisions in the field. So now next, let's try to design a pump for this well. Okay, so let's assume now that let's remove everything, and now let's go and you know, change the conditions. So my reservoir pressure has declined. So now the reservoir pressure is 2,100 only, and my water cut actually has increased. Let's say it was 500. My water cut has increased to 70. I am, let's say, 10 years from the first production. Now, if I go to my nodal analysis again, see how much I'm going to produce now. The well is dead for these conditions. See, there is no intersection between the inflow and the outflow. And it says unconverged flow rate. That means the well cannot flow under these conditions. What are these conditions? Again, reservoir pressure 2,100, productivity index 5, and the water cut is 70. The well is dead under these conditions. So now what do I need to do? I need to install a pump that will bring back my production to, for example, let's say 2,000. So how do I do that? I go to ESP design, an interesting task. Click on that. Now, it will ask me about the operating conditions. What do you want to do? So I tell him, I want the outlet pressure to be 250. This is my reservoir pressure. This is my, so all of this is taken from, you know, the current well conditions. But then I tell him, I want to produce 2000. So this is my desired production. Now, based on this, he automatically told me, okay, I'll put the pump at the end of the tubing. Now I can click on this button to see what are the available pumps that can give you this, that can give me this flow rate. So now I can select, for example, the one that I have a contract with, for example. Well, for the time being, let's use the first one, which is REDA. This is a Schlumberger pump. This is the series, the minimum flow rate, maximum flow rate, and this is the efficiency. When I click on OK, now it says, okay, I will install the pump, but now I need to know how many stages do I need to put. Okay, when I click on run, it will go and calculate for me everything. Okay, so now as you can see here, this is the original IPR. Okay, this is the IPR at different frequencies. Okay, and as you can see here, this is the IPR at 60, where I wanted to produce 2000. And now the result is 84 stages with 60 hertz. This is good efficiency. This is the power required at the bottom hole, right? This is the head added by the pump. This is the differential pressure. And now I can look into the actual pump performance curve. So this is the actual pump performance curve. This is the operating conditions, but this is at BBL. This is at flow, right? And now this is the nodal analysis after installing the pump. I'm happy. I can now tell him install the pump. So now click on install the pump. The pump now will be added here. See, it was added at the same depth. All that in simulation, right? This is very important for you. If you are a production engineer, you want to come up with a new ESP design. This is what you need to do. I have defined what is my where do I need to the well to flow, right? And then I selected from the catalog. Now I have installed the pump. Now if I go to my nodal analysis while the pump is installed, let me just show you. If I go to Inflow outflow sensitivity and I go to the pump, just to see the impact of the pump, I can put two frequencies. Frequency of 0 represents the pump is not rotating. Frequency of 60. And now when I click on run, see now, this is when the pump is not running. This is when the pump is running. And now, as you can see here, why I'm producing more rate. I was expecting to produce 2000 only. So let us see here. Yeah, because you see, it was reading the original reservoir pressure. You should have clicked reset boundary conditions. Again, 250. See, now the reservoir pressure is 2100. Now it should give me the exact rate, which is 2000. See, it is producing 2000. So this is when there is no, when the frequency is 0, when the pump is not running, and this is when the pump is running. Okay. Good. So I think I'm done. So let's open the floor for any questions.